All right, so now we're going to do problem number 1. You should try problem number 1 before I do it because it really is not that bad. But I'm going to go ahead and do problem number 1 now. So hopefully you pause this if you haven't yet done problem number 1 on 13.6. So here we go. Capacitor plates are arranged so they're 0.000010 meters apart, filled with air. What would be the area of the plates needed in order for the capacitor to have a capacitance of 2 pF? That's picofarads, right? So picofarads have to be beyond micro. Micros times 10 to the negative 6th. They have to be beyond nano, which is times 10 to the negative 9th. So pico's got to be times 10 to the negative 12th. It is on your formula sheet. If I get it wrong, well, you know that I should be looking at the formula sheet just like you guys. So picofarads times 10 to the negative 12th. So I'm going to go capacitance equals K, A, E naught, all over the distance between them. So K, there's no mention of what's between them, so we assume, it says what's between them is air. I'm not going to bother. Air is just essentially 1, just like space is. It's, it is virtually the same thing. A, I don't know, but it's asking what the area of the plates needs to be. E naught is our old friend 8.85 times 10 to the negative 12th. It'd be nice if I didn't chop off the 12th. I do apologize. Distance between them is 0.00001. And that's going to equal the capacitance, according to this, of 2 times 10 to the negative 12 farads. All right, it's just math from there, correct? So that should be a piece of cake for us. We go 2 exponent negative 12 times 0.00001 divided by 8.85 exponent negative 12 divided by 1, which is a little bit silly, but we'll go ahead and divide by 1. And I get that the area would have to be 2.26 times 10 to the negative 6 meters squared. That's the area of one plate. All right? And it should be small because we're talking about square meters and we're talking about little things that go inside of circuits, including things like integrated circuits that are so small you need a microscope to see them. So you should be able to do 2 without any problem. I'll do problem number 3 in just a moment. So when you get done with trying number 3, I will do number 3 with you. So go ahead and do 2 and then 3, and I'll catch up to you on the 3 side. All right, let's talk number 3, shall we? On number 3, a parallel plate capacitor, which has plates of 1.00 times 10 to the negative 4th meters squared, and the plates are in a vacuum. The capacitance is 2.77 picofarads. Calculate the value of the capacitance when the area is filled with neoprene rubber. All right, well, what does neoprene rubber do? It changes my K, right, which is in the formula. The rest of this is not going to change. The plate's area is not going to change. Its E naught's not going to change. The distance is not going to change, but the capacitance will change, right? We know all this is all this is 2.77 times 10 to the negative 4. Nope, that's a lie. 2.77 times 10 to the negative 12th because it's a picofarad. And so since that's the case, all I have to do is multiply that by my new K. So I look up neoprene rubber. You do not have to have these memorized. They will give them to you every time. Neoprene rubber I see is 6.7, so I'm simply going to multiply 6.7 times that number, 6.7 times 2.77, and I get a whopping, the new capacitance would be equal to 18 or 1.86 times 10 to the negative 11th farads. And so I make my capacitor 6.7 times stronger because I'm using neoprene instead of air in between the two plates. Isn't that fun? Not that bad. Shouldn't be that bad. Now I'm going to apologize to you because I say not that bad, and then I say let's try problem number 4. And 4 is going to be fun. So try number 4. You're going to get stuck. I would remind you to look through your notes in the previous video because all of it's there. It's just we did it for 2 plates. Now we're going to do it for cylindrical capacitor, so it's going to be a different sort of thing. Cylindrical capacitor, by the way, has two cylinders inside that are a distance apart. They're going to look something like this with another one wrapped around it. Okay, and the question actually refers to what's the inside radius of the outside. They give you the outside radius. Okay, so again, hint: you need to remember Gauss. Oh yeah, you need to remember Gauss. So pause this, look at the problem, try it a little bit, and then I will get you past the stuck point, wherever that might be. Okay, so the game plan for this type of problem is we are going to try to get to this place CV equals Q, right? And essentially C equals Q over V is ultimately what we want to get to. To get to that spot, we're going to have to figure out the voltage between these two things would be, assuming we could figure out a way to figure out what the charge on these things would be. And we're going to have to assume a charge because there is no charge. This is something sitting in the bin. So we're asking what would happen if it is charged. So we're going to pretend like it's charged to do the problem. So if it is charged, it has a charge per unit length. So we're going to do the same thing we did with Gauss. We're going to find the electric field between these two. So we're going to go EA. Again, I'm not doing this the formal way. We probably should spend a little more time doing it the formal way, but I have 15 minutes or 9 minutes left, and I have to do what I need to do. And this is E, the area of the shape I would draw between the two, which is a place where the electric field is relevant for in terms of voltage difference between the two plates, is going to be a cylinder. That cylinder, is, remember, is going to be 2 pi r times the length of the cylinder. And that's going to equal our old charge per unit length times the length of the cylinder divided by E naught. Okay, all right, so we roll through, we realize the length doesn't matter, which is something that we're excited about. As long as it's sufficiently long that it doesn't matter. And we get their electric field is going to be equal to lambda over E naught 2 pi, and this becomes r to the negative 1. To find the voltage, I need to integrate this, so I'm going to integrate it. A lot of this stuff is not going to matter. 2 pi r to the negative 1 dr. All this stuff can come out in front because it's all constants, and that's all good. But now I get to integrate this thing, and if I integrate r to the negative 1, I get ln of r, absolute value, plus c. But I'm actually going to do it from one distance, which is 0.0015. Actually, that's the outside distance. Let's go ahead and make it the outside distance. And the inside distance, which I'm going to label with a capital R. I actually did that backwards twice. Okay, let's try to do it right ways this time. Okay, so I'm going for the inside of the outside. Makes sense. Again, it would go the other way around if it's a positive charge, so I'm just really wasting time here, but yeah, you know what I mean. All right, so as we get so the inside would be 0.0015. The outside is the distance R that I would like to know something about. And so I'm going to then set this, so the voltage is going to be equal to lambda over E naught 2 pi ln of capital R minus lambda over E naught 2 pi, and then I'm going to get ln of this really nasty looking number. So that's my voltage, right? That is my voltage expression right here. Some things to contemplate, which we'll get to in a second. So if that's my voltage, and that's how I'm going to find my R, I need to figure out what my charge would be. Well, my charge is going to be lambda, my charge unit length, times the length of the capacitor, right? And so I can rewrite this as Q. Well, I can just do with a Q. That's fine too. I can do Q. Let's just keep going where we are. Okay, so CV. So C is 10 times 10 to the negative 12th times this ugly, ugly, ugly expression. Now I'm going to rewrite lambda as charge per unit length. So I'm going to go lambda equals Q over L. So that puts a Q on top and an L on the bottom. So I'm going to go Q over E naught, okay, 2 pi ln of absolute value of R minus Q over E naught 2 pi, need that L on the bottom again, ln of 0.0015, and that's going to equal Q. Well, here's something interesting. I can divide both sides by Q and make this 1. We know the capacitance shouldn't matter. The charge I put in shouldn't matter. It just changes our voltage, which was not going to be constant anyway. So now I've got everything I need to solve for this, and just spend a lot of time with our calculator, right? So we're going to do 1 divided by 10 exponent negative 12. I should have a length on this one too. Okay. So yeah, let's go ahead and do it that way. So I get 1 times 10 to the 11th over here. And then E naught is 8.85 times 10 to the negative 12th times, so I'm going to pull out all the constants. So I get ln of R, which is going to be a positive number anyway, so I don't know why I was waiting so long to fix that, like that. And then around this mess, I'm going to pull out all this other garbage, which is essentially 1 divided by 8.85 exponent negative 12, divided by 2, divided by shift pi, divided by the length of the thing, which I lost track of somewhere in the pile. It is 0.06 meters long. And so that I get that the number out in front here would be 2.997 times 10 to the 11th if I pull out all of the garbage, the 1 over E naught 2 pi L. Okay, divide that across, I get 1 to the 11th divided by that, so answer, and I get that ln of R minus ln of 0.0015 has to be equal to 0.334, essentially. Ln of 0.005, so ln of 0.0015 is, so I'm going to get my pen, ln of R plus 6.50 equals 0.334. Subtract the okay, wait a second, I'm going to take 0.334, 0.334, and I'm going to subtract the previous answer, and I get ln of R, my pen, ln of R must therefore equal negative 0.61, negative 6.17. So then I'm going to swing the E across. So R equals E to that answer. So I go ahead and E to the answer, and I get a number that makes very little, yeah, it makes some sense. Okay, good. I was about to say it's too small, but I get 2.09 times 10 to the negative third. If I move it 2 decimal places, I get 0.00209 meters. And that would be what the outside radius would have to be in order to make this capacitor. Okay, all right, there's a spherical one below it. Good luck trying that one out. You should definitely try it because it's fun and entertaining. And then we will adjourn this for right now.